Hello. Let's see whether the stream has started. Okay. So, oh, hello everyone. Hello, hello. Right. Okay. Hello, Uzbek. Hello, Ransom. You guys are the first people here today. That was really nice. Uh, Welcome to day 79. Wow. It's almost 100 days now. And afterwards we'll decide something else, right? But the streams are going to still keep going on, by the way. um so hello, hello. um Assalamu alaikum. I hope I said that very well. Yes, 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 yes. All right. Thank you guys for being here. I really appreciate you people. Also, not to forget, I just hit 1,000 subscribers, which is really not expected, but also kind of expected because uh, I was putting out content every day, which is really good. Anyways, thank you guys for subscribing to my channel and keep subscribing. Um, so today we are going to we are going to learn about trees, the trees data structure, which is something I started yesterday, but the stream went funny. But anyways, today's another day to learn. And after the stream, I actually did some work and tried to understand certain things. So I came back better than yesterday. So I'll be sharing whatever I learned with you guys today, which is, um, you know, like a good feeling, right? Because yesterday I did not know anything about trees, but today I have a bit of knowledge and I'll be sharing that with you guys today. Okay, so um the resources I posted in the description are still the ones we'll be using, so which is um you know useful for you guys to also try out as well. And yes, I'm not calling you. Sorry guys. So we can then study together today and share some knowledge. So if you okay, so Ransom is solving problems on dictionary, which is good. Okay, that's very nice. I want to create a Discord server. I've been saying this for the longest time, but today I will take I'll make that decision today. Create the Discord server so we can interact more. And when you have your questions that you are solving, you can post it in the Discord channel, and I'll try my best to help out and explain them to you as well. So Discord channel is coming soon. I mean the Discord server, so that you guys can join in and we can interact more. All right, enough of the introduction. So let's get started on trees. So trees are um, trees, just like trees. Anyways, they share the same property with linked lists, meaning they have nodes and each node has a value. So, and there is a connection between each node in the tree, and the expressions used in the tree data structures or the terminologies are quite similar to a normal tree in real life. So we have a root, we have leaves, we have branches, and and so on. But what we're going to learn today is to go over those terminologies, learn learn the basic stuff, right? And also perform simple operations like creating a binary tree, right? And also traversing the binary tree as well. Now, I've seen a lot of ways to create a binary tree, but a much simpler one um, that I came up with, right, or that I actually learned about is to, so there are a recursive way to insert nodes in a tree, but also there is, so since I've not done recursion in this on this stream in this 100 days of data structures, I did not think about introducing it at this point, but I couldn't help it. There was a point where I needed to put in recursion, but it's not a complicated recursion, at least for the insertion of node into a tree part. We are not using recursion at all, but traversal of the nodes, there's going to be a bit of recursion, but it's just a really simple type of recursion. Anyways, so let's get started. So I will remove this from here. Sorry, the chat might be closed for now, but hello, Manash. Yes, you're welcome. You're welcome from India. Thank you very much for being here and studying with us. Okay, so I'll just close the chat for now and go to the explanation board. And once I'm done, I'll come back to the chat and answer your questions. Okay, so let's see trees. I'll read again. This is a very good resource. I really like this article. It is more detailed, and there is also a visualization of certain parts of the tree data structure. Um, so I'm just going to erase the board now and take all of that out. All these the resources I'm going to be using today are in the description below. So if you're following along, you can read about them as well. You can come to this website. Anyway, so the tree data structure is similar to linked list, which is another data structure we've done previously. In that each node contains data and can be linked to other node. Like I said, so we have okay, you know what? Before we get to this place, let's read this part. We have previously covered. Okay, this is not nothing concerning us. This is just about the article and what they are saying. So this here is one of the most interesting things one of the things that we are interested in, which is the tree data structure. Like, I don't know, it might sound like a tautology, but the tree data structure has a way it is formed, right? Which is, in other words, the structure of the data structure. Yes. So we have nodes, we have linkage between nodes, and each node has a value, which is similar to linked list, right? If you remember very well, in linked list we have nodes, right? So I'll come here. We have nodes like this. So this is a node, right? This node will have a value. Let's say this is 1, and 1 will be connected to the next node, which is 2, and so on, right? So we can have 3 and 4 like this. So each node is connected to the next node, right, via the next pointer. But then again, there is something else. Each node has a name, right? At least there are certain parts to a linked list, right? The head node, I just said the name. The first node in the linked list is called the head, right? So this is our head node. This is the head node, and every other node in between is just, they are called nodes. But the last node in the linked list is called the tail node, right? It's called the tail node, and it is usually linked to null, right? So it means there is no more node attached to the last node. So this basically is the tail node, the tail node. So what this article is saying is, um, this property of linked list can be you know, related to um the trees data structure, right? So which is what we are going to read very soon. So let's cover that. So just like linked list, here we have connections. So the data structure is called a tree because it looks like a tree, only upside down. Okay. And just like the image we do. So here's a representation of a tree. I will just quickly write it out here. Uh you know what? So let's keep going. So the tree data structure can be useful in many cases: hierarchical data, file system organization models, etc. Databases. So you can use trees in a database used for quick data retrieval. Okay, that's nice. Routing tables used in routing data in network algorithms. So we have sorting and searching, used for sorting data and searching for data. Priority queues, don't know what that is, but priority queues data structures are commonly implemented using trees, such as binary heaps. Okay, that's nice. So here are the terminologies, right? Which is where I was driving towards. So we have a root. The whole tree is the entire connection between nodes and child nodes and so on. But the first one we have here, the first node is called the root node. And like I said, not me, but like as we read here, there is a similarity between linked lists and trees, right? So we have root node, we have edges, we have nodes, right? We have leaves, we have child nodes, we have parent node, we have the height of the tree, the size of the tree as well. So let's represent a tree here. I'll draw a tree like this. So we have a node. This tree has children. So here's the child. Here's another node here. And then each node has, other child nodes. I'll represent this like this. So there's another space here. So here is our root. Our root node is at this point. I'll call this A. So this is the root node. So this is the root. And similarly, in this case, we have a head node, right? This is a linked list. So we have a head node in the case of linked lists. And in the case of trees, we have a root node. So, and then there is a connection between the nodes, right? You can see in linked list we have similar stuff. So this node is connected to the next node and so on. So everything in the linked list, right? All of these circles here represent nodes, right? So these are all nodes. All of these are nodes, right? We have nodes, and currently we have about 7 nodes here, which I just drew. So, and each node is connected to the other node, and by through their connection, right, they possess certain properties, or we can call them they have specific names, right, through the way they are connected in the tree. So this node here, right, I'll call this B. This node here is connected, is a child node to the root node here, right? This node here is a child node to the root node, and this is also a child node to this root node here. Now both of these nodes, right, are children to the root node, and this is the left child node, right? Left child, and this is the right child. So this is the right child. And each one of these nodes, right, are also parent nodes, right? They are parent to all these nodes here. So we have, let me just pull D, E, F, G, right? So D and E are children nodes of B, right? And C is the parent of F and G. So, which is you know, let me erase this part so that I don't make a mistake. All right. So um here's a basic representation of a tree, right? And we can also have certain properties. Now, each one of these node, right, without children, will have, null pointers, right? Null like this. Because every node in a linked list has to have, the idea is that every node has to have a child, a left and a right child. And it just like the case of a linked list, when you look at the node class, right, of a linked list, it looks like this. So we have a node, and the property of the node is such that there is a value, right, for the node, and there is a next. Let me write it with a different color. So there is a value for the node. So we'll have um, the node's value, right, like this, and the node has to have a next pointer. Now this next pointer will be initialized to null at first, right, because it is not connected to any node yet. So once the connection happens, the connection will happen at this point, right? So we'll connect another node to this node. Let's say 1 here was the node we instantiated at first. So we connect a second node to this node here by simply assigning that node an instance of that node to the next value of this node here, right? So the next value would then have this as its own value. So the connection will happen like this. So after instantiating 1, we'll connect 2 to 1 through the next pointer, right? Which is this next pointer here. So it will no longer be null, right? When there is a presence of a node in the linked list, the connection will happen at the next pointer, at the position where the next pointer is. So now let's take a look at this part. Now, in the case of a tree, every node in the tree has a different kind of property, right? But they are actually similar. So let's take a look at the structure of the node in a tree. So let's say this is my node. So I will just put A here, and this node will first of all, let me just do it this way. So it points down, right? So this node has a right child, right? This is one of the properties. This will be set to null, right? In a normal state, right, the node structure will have a right child set to null. And here on the other hand, we'll have a left child. This is a left child. The left child will also be null, like this. The node itself has to have a value, right? At this point, I'm calling it A, but we'll have an actual value in application. So in practice, so we'll have A denotes the value of the node, right? So I'll put this as let's say, okay, so this is the value of the node, right? Value, like this. So in the case of a tree, the nodes in a tree have 3 properties, right? 3 properties. We have a value, we have the left child, and we have the right child, right? So every one of these nodes here will have similar properties, but once there is no connection, right, to that particular node, the left and right values will be set to null at first until there is a connection, right? Until there is a connection of another node to this node here, where the value is no longer null, right? So we'll change this here from null to an actual value. Let's put this as H, right? So until there is a connection here, this node has a left child set to null, and the right child will also be null at that point. So now nodes without child nodes are called leaf nodes. So here are the leaf nodes. We have this will be a leaf node. This is also a leaf node. So no child at all, right? When a node has at least one child node, it becomes a parent node, right? So all of these are leaf nodes. So let's move on with the article. So you can see now there is another thing to note is the um so I've explained leaf nodes. You can see when we click on leaf node here, all the nodes that have children nodes are grayed out, right? So only nodes without children are actually active or brightened up. So um here, so let's see, these edges are simply the lines we draw, right? The edges, I think the edges will be the, I won't call them the left and right pointer. Okay, let's say it's the left and right pointer, right? The left and right pointers to the children, not the children themselves. Okay, so the height of the tree. Now, when we look at this tree, right here, my representation in this case, when we look at this tree, to find out the height of the tree, right, we need to know the longest or the the farthest um the farthest node away from the root node, right? So in this case, we can count one, two, and three, right? So we have three nodes away from the parent node here. I think, and then we do the same thing, right? So we calculate for the right side of the root node, and then we'll do the same thing for the left side. Sorry, this is left and this is right. So we'll do the same thing for the right side, and then we'll find out the longest, right? And that will become the height of our tree. So let me quickly read about that. So in this case here, it's going to be it's going to be 2, right? The height of this tree is going to be 2, and just like I said here, the height here will be 3 in this case. So we went from A to B to from B to D, from D to H. So here this is going to be 3, and D on this side is going to be 2. So 3 is obviously superior to 2. So we choose 3, which is the highest value, as the height of our tree. So that is awesome. And yeah, so let's continue with some other stuff here. So these are just some explanation of the terminologies used here. So you can read through these as well. Yeah, so there are some. You know what? These are not really, you know, uh, this is very self-explanatory, right? You just read about the types of trees, explanation of the terminologies, like I just did now. So we have different types of trees, but we are just going to cover binary trees for now. Trees are fundamentals. Are a fundamental data structure in computer science used to represent hierarchical relationship. This tutorial covers several key types of trees. So we have binary trees, which is what we are going to cover, right? Each node has up to 2 children, the left child node and the right child node. This structure is the foundation for more complex tree types like binary search tree and AVL trees. So we are not going to do AVL trees and binary search trees at this point. So let's move on to binary trees. So we have binary trees, which is what we are covering today, basics of binary trees. So in a binary tree, like I said, so which is what we have here, this is a representation of a binary tree. Now you can see each node has maximum of 2 child node, right? Binary tree, binary is 2, so we have 2 child node for every node or for every parent node in a tree. So a binary tree is a type of tree data structure where each node can have maximum of 2 child nodes, right? So maximum of 2 child nodes. We have a left child node and a right child node. So this is really nice to read. Um, so this restriction that a node can have a maximum of child nodes gives us many benefits. So algorithm like traversing, searching, insertion, and deletion become easier to understand and to implement and run faster. Keep Keeping data stored in a binary search tree makes searching very efficient, which I agree with, right? Because yesterday when I was learning about trees, I just realized something else, something I will be sharing with you guys. But for now, just keep it in mind that searching for a value in a binary tree is a lot more easier, right? I know there are arrays. I mean, when an array is sorted, right, um, you can easily find a value you are looking for. But in the case of a binary tree, it becomes, it's like a binary search, right? But done in a different dimension, which is in the tree data structure in this case. So, um, balancing trees is easier, right? To do with a limited number of child nodes using AVL binary tree, for example. Don't know what AVL binary tree is. So, binary trees can be represented as arrays, making the tree more memory efficient. I don't really agree with that, but anyways, arrays take up a lot of space in memory, so let's not be nice. I mean, let's not sugarcoat the fact that binary trees is using arrays, and then now all of a sudden it becomes memory efficient. All right, so let's see. Use the animation below to see how the binary tree works. We've seen that already. So now you can see we have a root node, obviously, which is the head node here, which is R. R is the root node. The left, um, A's left child will be C, right? You can see A's left child will be C. A's right child will be D. B subtree will be everything here. So a group of trees underneath a particular node will be called a subtree. So, so this is the B subtree here, right? And the tree size is equal to 8. Let's see how. So wait, the tree size is every node in the tree, right? All the node in the tree will give you the size of the tree, but the height of the tree is the longest I'll say the longest path down the towards the last or to the last node in the tree on either side, right? And by either side I mean the right child of the root node and the left child of the root node. So you can see tree size is every node in the tree. Tree height is the longest node away from the root tree, right? And child nodes are all the nodes except the root and parent or internal node. Mm, this is good. So yeah, so you can also read about this. I will read all of it now. I've actually read this, so you can read this as well to understand what's going on. But um, you know what? Let me just read it. Binary trees versus array and linked lists. So there's a comparison being done here. And it says arrays are fast when you want to access an element directly. Like an element, um, like element number 700 in an array of 1,000 elements, for example, right? But inserting and deleting elements require other elements to shift in memory to make place for the new element or to take the deleted element's place. And it is time consuming, which is true, right? So insertion in arrays are notoriously time consuming. So it will take O of n time complexity to make an insertion of a value in an array, which is what it's saying here. I've read that, some time ago. So if we have 1,000 elements in an array and we want to delete let's say the 700th element, right? After deleting the 700th element in the array, every other element in the array has to shift, right? So everything has to reposition themselves so that there is one less than 1,000 elements in the array. So this is going to take O of n time, and n denotes or represents the amount of elements in the array. So if there are 1,000 elements in the array, when you delete one, 999 uh, 999 elements have to reposition themselves, right? Which you can imagine that's how time consuming that is. So linked lists are fast when inserting or deleting node, which is true. Inserting, I'm not sure. Inserting a node in a linked list, uh, nope, I don't agree, because uh, it's going to take O of n time to insert an item in a linked list. So I don't want to. I'm not sure if that is fast in the case of a linked list, a data structure like a linked list. But anyways, um, deleting a node in a linked list is obviously not difficult. You simply need to replace the uh, previous node's next pointer to the node ahead of the node you want to delete. So, and then you just delete it like that. So there's no repositioning of nodes in a linked list. So, which is good. That will happen in constant time. So deleting is fast. No memory shifting needed. But to access an element inside the list must be traversed. Yes, so the list must be traversed in order for us to insert an element in the linked list. Now, in a binary trees, right? Binary trees such as binary search trees. Binary search trees. Interesting. And AVL trees. I don't know what AVL trees are, but I'll find out sometime. Anyways, AVL trees are great compared to arrays and linked lists because they are both fast and accessing a node. They are both fast at accessing a node and fast when it comes to deleting or inserting a node with no shifts in memory needed. Interesting. So, we will take a closer look at how binary search trees and AVL trees work in the next 2 pages. But first, let's take a look at binary tree, at a binary tree, how a binary tree can be implemented. Okay. So we have this here. The implementation I have done already, and I'll share that with you guys, which is one of the things we'll cover today. But yeah, so let's read this part. I think these are just like types of binary trees. We have a balanced binary tree that has at most one indifference between its left and right subtree height, sorry. So a balanced tree. For each node in the tree, for each node in the tree, there's a difference of one, right? The tree has at most one difference between its left and right subtrees. We know what a subtree is, right? So a subtree can be, from here all the way down. So from B to, G. This is a subtree, right? This is a subtree at this point. Sorry, what was that? Oh, Microsoft. So this is a subtree here from B all the way down, and we can find out if a tree is balanced if there is just one in the one difference in the height, right? So let's take a look. You can see here this is a balanced tree because this has just one extra node from its left and right node. So the difference here is one. And complete and balanced tree is here. So in this case, you can see this node has two node, which would have made it balanced, but this also has another node. Let's read that and see what it is. Complete binary tree has all levels full of node. Okay, okay, okay. So except the last level, which can also be full or filled from left to right. The properties of a complete binary tree means it is also balanced. A full binary tree is a kind of tree where each node has either two or zero nodes. So either zero or two child nodes. So let's say a complete a what's this? A full binary tree. Okay, so this here, okay, so there's no balance to make here. So which means this node has at least zero child or full child. So it has to have either two children or none. So which means it's full. Okay, and there's a full, perfect, balance, and complete. Um, okay, so there is our full, perfect, balance, and complete binary tree, which is this part here. Um, you know, this is another visualization. This resource is actually very good for us to use in understanding what trees are. So, da, da, da. So let's see what we have here in the chart. I'll just open the chart and see if there are any questions. So okay. Uh, yeah, yes. Hello, yeah. Yes, trees again, trees again. Uh, I see my family tree this tree. Okay, that's really nice. Oh, thank you, Manash. Thank you. I really appreciate that. Thank you, thank you. Um, that's very nice. Hello, EW. Yeah. All right. Thank you guys. I like the way you are interacting. Uh, yeah. Uzbek said it's the family tree. Nice. Okay, so this is good. This is good. So let's pass on to write some code about trees, and see how we can implement trees in terms of code. Yeah. So we are not planting a tree. Okay. All right. Let's go here. Let's come here. How many? Okay. So I've done 30 minutes so far. I didn't change my time from the weekend, which means it is usually set to 2 hours, but I'll change the time here to 40 minutes or 45 minutes for weekdays, or let's say an hour. Let's put an hour. I might finish before an hour, but let's leave it as an hour for now. Scene, um, scripts. Let's change this to 60 minutes. All right. So yeah. So I was implementing a tree here, but I'll go through again and explain. So let me use my playground to explain this part of the trees implementation. Now we know a tree is made up of nodes, right? So we'll create a node class. We'll create a node class, and then we'll create the implementation of the insertion. We'll write code for the insertion of nodes in a tree. Now there is one thing I want to also explain, right? Uh, so in a binary tree, the binary tree has a very uh, strange property as concerned with the insertion of nodes in a tree, in the binary tree, right? So as you all know, binary tree has two child nodes at most, but the left and right child node have a little bit of I would say there is a subtle difference, right, between the values that are inserted in the left and child node. So the left child node would have values less than the right child node, right? In other words, all the values on this hand, right, have to be less than the value on the right hand side. And that's the same case for every child node of the of a parent node, right, or in the subtrees. So here we have this D value has to be less than the E value, right? And the reason for that, I will explain why it is done that way, but I just want to really clear that out. I've not seen an implementation, an actual value insertion of um, so we can actually know how it looks in real life. Let's see binary trees. I think here we might have, let's take a look at some images. I want a binary tree, so let's say binary tree. Binary trees. I mean, this tree here is wrong, by the way, so this is not how it's supposed to look. Every value on in the left subtree has to be less than every value in the right subtree. Yeah, so with this I can agree. So this is an ideal representation of the binary tree. So I can accept this one. So you can see the root value has here we have 45. Okay, that's a white color. This is 45, this is 15. 15 is less than 45, so it is inserted on the left, right? And 79 is superior to 45, which means it has to be inserted on the right. And the same thing happens in the subtrees, right? So 15, the next value we want to insert, if the next value was 10, right, the next value has to go on the left hand side of this 15. 15 becomes it's literally like the root now, right? Which is why they call this from this point all the way down. This is a subtree, right? So there's levels to this tree. So meaning from here all the way down, right, the insertion has to happen in that same order. So every value that is being inserted, as long as the value is less than the root, right, we shift all those values into onto this side, right, and then the insertion will happen the same way, right? So if we are on this point, if this node here does not have all its child nodes, right, in other words, if the left and right child nodes are still empty, we make the insertion the same way. So this is 10, right? So we want to insert 10 into this tree. So to insert 10, we have to first of all find out if 10 is less than the roots, right? So the insertion has to happen in order, right? Skipping every node until the point where there's a vacant space for the current node to be inserted in the tree. So which is what happens in the tree. So let's say I want to insert maybe a 5, right? This is 5. 5 is less than 45. So meaning 5 will go on the right on the left on the left side of this tree, right? So we'll check again. So this part here, meaning 5 will go on the left hand side. And when we're at 10, right, this is a child node. So 10 already has 12 as the right child node. I don't know why the insertion was made here, because when the value is normally when a node has no value at this point, right? Okay, sorry, 12 is superior to 11, is superior to 10, meaning 12 can go on this side. So since 5 is less than 10, 5 gets inserted at this point here. Okay, this is right, sorry. So and let's say we want to insert a 100, right, into this tree. So 100 is obviously superior to the right the root, so meaning 100 will go to the right subtree, right? So, and when we get to the right subtree, we have to compare every value in each node. So here we have 79. 100 is superior to 79, so 100 is going towards this direction, right? So, and then 90 is still less than 100, so meaning we'll insert 100 at this point as the right child node of this, right? If we're inserting, let's say, maybe an 80, right? 80 is superior to 79, so it's still going to come to this side, meaning it will become the left child node of this 90 node here. So we'll have an 80 here. Okay, so this is good. I just really want to clarify that. And let's go back to the basics. I'll come here. Let's refresh this part and see if there are any questions in the chat. Let me bring this chat here. Okay, so there are no questions. Okay, that's all right. That's fine. That's fine. This cracks me up so much. They say, "Oh my God, trees again." Okay, yeah, we're going to do trees for a while now. Okay, let's go. Let's start. So no questions. Let's first of all, we need to create a class, a node class, right? You know what? Let's call this tree node. Tree node. Think I saw a question on Let's Go that they use tree node also. Let me say binary search tree. Yeah. So it's called tree node. Yes. So they call it tree node, which makes it easier for us to understand. I mean, actually, easier to recognize. So we'll use a tree node. This is a tree node, right? We'll create a tree node class, or we can simply call it a node, right? We know we are using trees, so let's just call it a node. So this is a node, and we know a node has three properties, right? It has the right child, the left child, and a value. So when we instantiate our node class, right, we need an init function to instantiate it. So we also need to pass it a value, right? In some places you will see this called keys. Let me put value there. So this is value, right? You'll see this called keys. I don't like using keys because it doesn't make any sense to me. Anyways, so I use values instead. So let's say I prefer the values way of writing the value. So this will have a right, which is going to be null at first, none, and a left, so self dot left which is going to be equal to none as well. And then we'll need a value for our node, right? We'll need a value. This is going to be equal to the val that we insert here. Okay, so this is all we need for our nodes. So these are the nodes that will be inserted into the tree each time we try to insert a node in the tree. So this will be instantiated all the time, right? This will be instantiated all the time. And like I did here, so let's see, you can see we have a right set to none, left none, and so now we have to create our binary tree class so that we can begin to insert values into the tree, right? So I'll call this class. This will be binary tree. Okay, so here is the class we instantiate to create a binary tree and insert nodes in the tree. So there is something we need to do. First of all, we need to create an constructor function, which is the init, right? Now we don't give this any values yet. We only need to create our root at this point. So this will be self dot self dot root. So we need a root for our tree, At first our root is going to be none because we don't have any values at this point. So now we will write a function to insert node into the tree. So first of all, let's create the function. So say if let's define insert node. Okay, let's call it insert node. So this is the node we want to this is the function, and the value we want to insert, right? So I'll just put value there. Now when we insert a value in a tree, it means we are inserting a node into the tree. So we'll have a new node. So a new node, which is an instance of the node, right? New node, this is going to be equal to the node class, right? The node class, and we'll pass it the value of the value we want to insert into the tree, right? So let's see what we can do here. So let's go on now. Just like in linked list, when we are inserting a value into the list, we need to ensure that our at least our head has a value, right? If the head does not have a value, we need to set a value. If the head is not a proper node, in other words, if the head is none, if the head is empty, then we need to insert a head in the node, right? So this is what we'll do in this case. So we'll say we'll first of all check if self dot root, right, is none. You can just do it like this. Then we can set self dot root to the new node we want to insert in the tree. Self dot root is equal to new node, right? And then we return this. Now I just write the return to just stop the iteration, right? To just stop the rest of the code from running. So in this case, if this was true, if this here was true, if the root was none, then we make the current root, right? We make the root of this class the new node we are trying to insert in the tree. So now let's move on to the next part. Now this is the interesting part where we begin to insert node at the appropriate positions, right, based on the node's values. So let me show you what I did here. First of all, we need to check if the root is empty. Now if the root is no longer empty, we can then set the current node. This is very similar to how I did it in linked list, right? So the same thing will happen in this case. So we can set the current node to the root node and then iterate, right? This is like just the way we traverse a linked list, the nodes in a linked list, until we get to a point where the current node we have now no longer points to a value, right? Which means the last or the tail node. So until we get to the tail node, then we set the value at that point. So the same thing will happen to this in this case, but in this case we are comparing values instead. Like I said here, right? Just like I said here, every node has to be inserted based on their value, right? So we need to compare the values and insert the nodes at that point. So if the current value that we are trying to insert into our tree is less than the root, it means it's going to be in the right subtree section. It's going to be inserted at that position, right? Otherwise, if the value is superior to the root, then we make the value go into the right subtree, right? So which is what we'll do in this case. So we'll compare the value, right? We'll say if the current value, right, the value we are trying to insert into our tree is superior to the node, the root node, then their value goes into the right subtree, right? Otherwise we just move on to the left. So let me bring this back here. I think I have a question in the chat, so I'll quickly have a look at that. Let's drag this here. Where's this? So refreshing. Da. Ah, this internet is slow. Okay, so somebody said, "Hey, bro, I got a super nested JSON, and I'm trying to create a dynamic function method of a class to read it. Can you give us an example?" I'm not sure what you're trying to ask me, but like, can you, if you have a link to the question to your problem on GitHub, I think it would be nice to share it so that I can have a look and see what you're trying to say. All right, and that was Gabriel. Gabriel asked the question, so I'm waiting for Gabriel to get back to me on that. Okay, so let's see. Now, in this case, we can run an iteration to insert nodes in the linked list, right? So say while true. Now, while true is simply going to end if we break the loop, right? In the case where we break the loop, otherwise this function um will run forever. So let's see. Um, so while true, we can have. So first of all, we need to set our current node. I'll say current current node current underscore node is going to be the root, right? So self the root. This is what I need to do here. And then while this is true, while it means while we are still in the loop, while the loop is still going on, we can say if the value we are trying to insert in the in the tree, sorry, if the value we are trying to insert in the tree is superior to is less, so let's do the left hand side first. So if the value is less than the current node dot value, right? I think I put val, right? Oh, okay, value. Current node dot value, right? Then we need to also check, right, if this is the last node, meaning if this is the last child of that node, right? Then we just say if current node dot left, right? If the current node dot left is none, right? We insert it here. So we insert it at this point. So we say current node dot left, right? Current node dot left should be equal to our new node. So I will just say yeah, it should be new node because we created an instance of the node here at this point. So on line 12, so we'll do new node. Otherwise, and we end the iteration here. So we break, meaning we've inserted it. Otherwise, else we'll just move on to the next. So we'll say current node should be equal to current node dot left. So meaning we are reassigning the current node to the left node, right? Because we need to make sure that the nesting happens on the left child, on the left subtree, right? So otherwise, if the value is superior, right, else we just do this. We say else if the value is superior to the current node, we'll do the exact opposite in this case. So we take the current node dot left dot right. So everything is here. It's still going to be the same, right? Like just sorry, it's still going to be the same at this point. You can see it's still the same. Left node is none. We set the left node to the new node and break. And in this case here, we are just going to do it on the right hand side, exactly the same thing. So and let's just continue. So we'll say if the current node dot right, not right, I will also walk you guys through what is happening under the hood, right, of this insertion. It is very important. Although my time is up, but I'll quickly write this code here to for you guys to practice with. So let's say if the current write is none, right, then we insert current node dot write should be equal to the new node, and then we break. Now this code will work for both both side of the root node. It just depends on where the value became superior at the current node. So became superior to the current node. It just depends on that, and then we know it's going to be either on the right hand side of the child node or the left hand side of the child node. So let's break here. Else we can do this. We can say current node is simply current node is going to be the right node of the current node. So current node dot right. Okay, so this is all we need to do to insert values in the tree. As you can see, this is very similar to what we do in the case of a linked list. In the case of a linked list, although we don't need to write all of this, we simply need to check if the current node has a next value, right? If the current node has a next value, otherwise we just set the next value of that node to the new node we want to insert in the linked list. Let me quickly show you how that is done. I've done it some time ago. So so let's see. Oh, this is a doubly linked list. Linked list here. So where's the basics? Yeah, so you can see to insert values in a linked list. Let's see. Yeah, so here add item. I think add node. You can call it whatever you want. So to add the node, we can just do this. You can call this current node. So like we are setting the head, right, the root node as the current node, right? We'll just do the same thing here. So we set here the head, and then if the head node, right, or the current node has a next node, right, then we set it to the next node. Otherwise, we set the next node of the current node to the new node. Okay, so I think let me check the chat again if there are any questions. I've been talking for some time now. Lopez said try to pass it. I still need to see a code, right? If you have it on GitHub, that would be really nice. You can share it to me. Yeah. Teacher. My name is Wilfred, by the way, Wilfred. So you can call me Wilfred or Will or Wilfred. Wilfred. Yes, this is my name. Anyways, you said will I be continuing making the tutorials when after these 100 days? Let's say yes, I'll keep making videos. So I'm planning something new. So we'll actually, I'll share that with you guys. I will not stop making tutorials, by the way. So it's still going to be an interactive stream going forward. So yeah, to answer your question, Uzbek, yeah. So I'll have more tutorials coming up. We can do more stuff. It's not just going to be data structures and algorithms. We'll learn a lot of things, even building projects in languages, building awesome projects. I think I have like a list of projects that I want to build, so we'll build all of them together here. Yeah. So we'll try and land a job. Yeah, that's also true, but it's not going to be this soon because I'm already working on some personal projects for now. But yeah, it's good. So let's see. Is he within my son after me? Yeah. Okay. When you have your son, let me know. Okay. Good luck. All right. Okay, so oh, oh my god. That was really nice. That's nice. Okay, so now let's visualize insertion of values into a tree, right? Um, insertion of values into a tree, so we can round up for today. My time is up. Um, so insertion of values, right? Let's create a tree. I'll write a random value here, some random values. I'll have like 10, or let's put 100 here, and then 10, 99, 50, 104, 108, um, let's say 200. Okay, so here's a list of values that I would like to insert into a tree or create a tree with. So here's what's going to happen with my implementation of the tree here, right? Uh, with my implementation of the tree here, which is this, we can um we can just visualize this quickly. So here's what happens. First of all, we need to check, right, if our root has a node or not. If it doesn't have a node, then we need to set the current value that we are trying to insert into our tree as our root value. So in this case, um, we can have the root here. So our root will be this. So we start here, right? Let me use a different color. I would like to use this color. So our root will have 100, right, which is the first value. So then our root will begin to have children nodes, right? So here we have the right and left child. Again, it's a binary tree, so we need to have right and left children. So where do you think 10 will go? Now, based on our implementation, based on the function, right, 10 will go to the left because 10 is less than 100, right? So 10 goes to this direction here. So this is 10. And 99. Now, 99 is superior to 100, right? The entry of our tree is always going to be the root, right? So we need to check for the root first of all. Now, 99 is superior to is less than 100, right? Automatically we know in which direction it is going. It is going to go to the the left hand side because it is less than the current the root. So when it goes to the right hand side, it will meet 10 here, which is another node waiting for it. 10 will also have either left or right. Now based on the value of 99, we will then insert 99 as either the right or left child of 10. So 99 is superior to 10. Obviously it is going to be the right child of 10, right? So we'll insert 99 at this point. So 99 will be here, and then we have 50. Again, 50 is less than 100, so it means it comes to this side. And 50 is also superior to 10, right? Meaning 50 will become a child of 99. Now what kind of child is it going to be? Is it going to be the left or right child? 50 is less than 99, so 50 becomes the left child of 99, right? So this is a random tree I'm trying to create here. So you can see so far, right, we are inserting values on this side, right? We are inserting values on the left hand side. As long as those values are less than the roots, we will then decide, right? We'll then decide whether it is going to be the left or the right child, right, of the left child of that particular root. That's a mouthful, but basically here's what is happening when we are trying to set a value, right? If we already have a root, right, we set our current node to the root and then compare the value to the value of the root. Now if this value here is less than the root, right, we then assign. So if the root does not have a left, right, if it does not have a left, then we just directly connect it to the left. But if the root has a left hand side, right, meaning we have to change our current node again to either to become the left node of that root, right? So once it becomes the left node of that root, this function will be called again because this iteration is still happening, right? So this will, as long as this is true, as long as we don't end this iteration, we'll keep performing all these operations here, right? So the current node will no longer be in this case 100, it will now become 10, right? Because the value that we are trying to insert at this point, which is 99, is still less than 100, right? So our function will do this. We'll assign our current node as the left, right? So left, our current node becomes the left, which is here, right, at this point here. So 10, we are trying to insert 99 into the tree at this point. So 99 is still superior to 10, right? Meaning this part here would no longer run. So this part will run at this point. So again, 99 is superior to 10. So 99 goes as the right child of 10, right? And we insert 99 at this point here. You can see here. So now let's go forward to these bigger values, which is 104. 104 is superior to the right the root node, so it goes straight to this point because there's no check, there's no right node here. We simply insert it at this point. So 104, right? And then 108. 108 is superior to the right node. So where do you think the 108 will go into? Well, 108 will become the right hand child, or the right child of this 104, right? So we set it here. This will become 108, and the last value we have here will also be the right child, right, of this 108, because it is superior to 108, it is superior to 100, it is superior to 104. So it goes to this point here, 200. So here's what we have. This is a representation of these values here as a tree. I mean, it might not be a perfect tree at this point, but I'm just trying to show you what happens under the hood with the insertion function. Now tomorrow we'll continue with more operations like traversing the node, printing out every values in the node. But one question you might have now is, we are making insertions from left to right? So if the value is superior to a node, we set it as the right child of that node. If it is less, we set it as the left child of the node. But what about the case where the value is equal, right? Let's say we are trying to insert another 10 into this tree. Now in binary trees, we don't have duplicates, right? It is going to be impossible to insert it here, so this will not work. So we don't insert values that are, every value in the tree has to be distinct, right? In short, every value has to be distinct. So let's do that now. So I'll push this code to GitHub, right? This version is also here. You can look at the binary trees folder, and you see the basics here, which is this. So you can have access to this code here. So you don't I'll push this to GitHub, and you can follow through, read what happens behind the scenes. Anyways, let me push this to GitHub. So git add git commit. I'll say this is binary trees basics, right? So I'll say git push origin main. So I did some traversal already. I studied some traversal. We'll look at this tomorrow. Just because I'm running out of time, you can try this out, right? There are some functions here. I even implemented the whole thing for you to test out. This is what I did when I was studying, so you can also try this out as well. Anyways, it's been nice streaming today. This stream went absolutely well. Thank you for all the participants. Let me check the chat if there are any questions before I leave. Um, so refresh, refresh, refresh. Uh, so okay, yeah. Okay, so do you have other social networks? Yeah, I think my Twitter is linked in the description of this question. Let me see. Yeah, so my Twitter account is here, my LinkedIn is here, but I prefer, you know what? You can contact me on Twitter for now, and going forward, you know, you can contact me on Twitter. Yes, you can contact me on Twitter. I would. It would be really nice to contact on Twitter. Yeah, so you can reach me on Twitter. I'll create a Discord server, like I said. I'll try to do that maybe today or tomorrow. Uh, yeah. Oh, you don't use Twitter? Okay, we can LinkedIn. How about LinkedIn for now? Before I create the Discord server, maybe by tomorrow we'll have a Discord server so we can talk more frequently. Yeah. A Telegram account. I don't have a Telegram. Oh, okay. Wow. That's sorry, bro. Um okay, okay. I'll create a Discord account. Telegram might not really work because I don't use my phone that very often. So, yeah. Um yeah, so yeah, we have Telegram here. Oh, you don't have Telegram on your site. Wow. Oh, okay. Instagram is so distracting, right? When I go on Instagram, I don't really, I just, it's, I don't know, it's time consuming. So I don't really use Instagram. I don't really use Instagram. So I already added you to LinkedIn. Oh, wow. Thank you very much, Gabriel. And he followed me on GitHub as well. Wow. Thank you very much. Thank you. Thank you. Um, Yes, I am African. Yes. I'm currently in Nigeria. Yeah, I'm currently in Nigeria. Um okay. So I think ransom is from Russia. Yeah. Ransom is Russian. Um so maybe I said Nigeria. I am currently in Nigeria. Yes. Nigeria, Nigeria. It's in Africa. It's West Africa. Um, we can try Discord, right? I'll create a Discord account for us to, you know, interact more. So we'll have Discord account. Yeah. Uh, so Uzbek, if you have Twitter, you can connect with me on Twitter. You can also uh on any other platform that I have linked in the description as well. Gabriel, thank you very much for following me on GitHub. That's really nice. Okay, guys. We'll continue tomorrow, and yeah. No more question. No more question. Okay, we'll talk more on Discord. Let me try and set up a Discord account for us, so that you guys can even interact with each other as well. All right. Take care, guys, and I'll see you tomorrow. Bye.